All right.
Start your presentation.
All right. So what you definitely need for this hobby to start off with is a good mount, a telescope or your lens, and a camera. Really, that's the bare necessities. Now, at least in my opinion, the mount is the absolutely most important thing because I've taken good telescopes on bad mounts, and I've taken bad telescopes on good mounts, and I'll take a terrible telescope on a great mount any day. I've taken decent shots with my $100 guide scope, on my CGM DX, and I've taken, pictures from my triplet on, you know, more or less a glorified tripod, whatever. And if you don't have a steady mount that you could properly polar align and it could run equatorially, then you're gonna have a terrible night. So here's a couple of things that come along with these. Now these aren't exactly necessary, but let's see. Okay, so there's the two main types of mounts that are out there. So you have the equatorial mount and your alt-az mount, or altitude and azimuth. Now what's the difference between these two? Equatorial will only move in one direction when it's tracking the sky, and this is absolutely mandatory when you want to do long exposure, deep sky object stuff. Altitude azimuth moves, left, right, up, and down to track through the sky. Now why is that a problem? Because when everything tracks from east to west in the sky, you want to have your camera and lens at the exact orientation that that object is moving. So if you were doing, if the object is going from here to here, and you're using just say a regular tripod, which is an altitude azimuth, you're gonna moving it up and moving it down. So you figure by the time it rose over here to the time it's set over here, everything is upside down. So okay, what does that mean? You're not going to take a 12-hour long exposure, but you'll take a 2-minute exposure, a 5-minute exposure. So your center. So here's a little a little animation I try to make. So it's the best, not exactly the most accurate representation, but in the center is what your camera would be doing. So everything will stay in the frame, and your center will be exactly centered as long as your tracking is good. But everything is going to start to blur, and this is what they call field rotation. So you could shoot with an altitude azimuth mount, but depending on where you're shooting and the focal length you're shooting, you're really going to be limited to maybe 30 seconds or so. Now you could do some great work in that time, and especially with the newer cameras, but you really can't go for deep, long exposures because, like I said, everything in your center will be pinpoint, and the further you get out, it's just going to look like a big spiral, like big star trails that you're going to come out of there. All right, so equatorial. This I actually just purchased recently for my mount because it doesn't come with mounts, which is kind of sad. But in the equatorial mount, you're going to have to align it at the North Celestial Pole because the Earth is pointed at the North Celestial Pole. So when everything is tracking through the sky, it's really just the Earth rotating in the opposite direction. So what you're doing with the equatorial mount is pointing it straight at the North Celestial Pole and telling the telescope, okay, to go backwards. So the Earth is moving this way, you want to go the other way. So you want to keep everything exactly centered. It's a little easier said than done, and there's 100 different ways that you could align it perfectly. But one of the simplest ways is to use something called a polar scope. Now, in the equatorial mounts, there'll be a hole from the bottom up to the top that you could actually look straight through. And you'll see that with the ioptrons and whatever. They come with the little polar scope that you could see. Yeah. So, but none of the bigger scopes, at least on the ones I've seen, ever come with it. Now, the reason why I never got it, not that it's very expensive, I think this one cost me maybe $40 or $50, is that I rarely have a view of Polaris, of the North Celestial Pole, depending on where I set up in my backyard or where I am in the Staten Island Park or so. So I'm like, okay, well it's cool, but I rarely see it, so it's not going to really help me at all. Now with the newer mounts, they're all electronic, so you have your own ways of aligning. So with my CGEM, you plug in a couple of stars on the east or west, and then you plug in a few more stars on the opposite hemisphere. So it really gets a good idea of where the telescope is pointing. And then you could ask it to help you polar align. So it has a function. But before then, so my father's old wooden mount, so all made out of wood, had the polar scope. So this was kind of your only routine. Otherwise, you wanted to spend a half an hour to an hour to do something called drift alignment, and that's very tedious and time consuming. So something like this is very helpful, especially at our magnifications. If we're going to shoot at 2,000 millimeters, 3,000 millimeters or so, you really should be as spot on as you could possibly get it. If you're shooting with the maybe a telephoto lens or so, you could get away with a little more shoddy work. So this is the view that I would get when I first set it up. So Polaris is not exactly at the North Celestial Pole. It's a little offset. Now the only problem is where on this circle do you put it? So I kind of get an idea of where the Big Dipper is. So nowadays the Big Dipper is somewhere like here. So I just twist the axis and then I try to get Polaris. Now that's another reason why I didn't get it, because this is not 100% foolproof. There are actually little set screws here, 3 set screws, which just because it fits in the axis, your axis is pointed this way and then the polar scope is facing this way. So then you got to spend a good hour or two, twisting it this way. Okay, dial it in. Now twist it that way. Now did the tree move, left and right? And then you got to sit there and dial it in. So, but this will get you really close, close enough. Certainly close enough for my triplet, which is only about 350 millimeters. But I couldn't use just this when I shoot at the 2000 or 1200 with the focal reducer. So this I'd say is a pretty good purchase if you were going to get an Equatorial Mount to get a polar scope with it, because it'll just give you a little bit better of a time. So it gets you close enough, and then the mount will let you. A really cool toy is this. Now this just came out recently. It's called the Polemaster. So instead of a polar scope, because you all know with this hobby, it's in the middle of the night, it's either freezing cold or burning hot, and now you have to sit on your hands and knees because the mount's just about right here, and then you're sitting there, and then you're trying to adjust your right ascension knobs and your declination knobs just to get it lined up perfectly, and again, kicking the mount and all that stuff. This is just like putting a camera in the polar scope. So this comes with the software and everything. So now everything is on your laptop screen, and it gives you the instructions. Okay, twist the mount right, twist the mount left, and then it gets a good idea of where the camera is. And after this, you really don't have to do anything with the mount. You could set it up for your star pointing and stuff, but just for the $270, I would say that this is well worth it. And of course, it's back order waiting list for a long time for this. But
you wouldn't have to do the various star alignments?
No, the only reason why I would do something like that is to give your mount an idea of where you're pointing. So if you wanted to hit a deep sky object that you definitely can't see with your eye, then you plug in your 2 stars and then you're out. You're free to go. But after that, no, I wouldn't do any polar alignment. Just enough to get you that you want to take a picture of something. Like if it was M42, Orion's Nebula, so you could pluck out with your eye, you wouldn't even have to bother. Then you just go to it. It'll be tracking just fine. So I think this one is it's a fantastic toy. But again, the downfall is you need to see the North Celestial Pole. So you can't just go, just set it up wherever you want and a giant tree in your way. So if that is your problem and you're surrounded by trees, like pretty much I am, there's plenty of software out there. Even SharpCap has their own polar alignment feature. You could always do a drift align. PhD, the auto guiding software has a function to do it as well. That works very nice. And I messed with that a few times. So, but like I said, this is all centering around the mount. So you didn't even mess with telescopes or anything yet. So mount perfectly aligned, you're going to have a lot easier of a time to take your images. This is necessary if you're going to do some field work. So I really don't mess around with these too much, but I had to get one for whenever we do stuff out in Staten Island or anywhere out in the field. These last forever though. They're not incredibly expensive. I have the one on the right here. It's only 7 amp hours, but I've already been using it for 5 years, 6 years or so. Never once has it died on me. I have to sit there for 3-4 hours at the Staten Island Park. Never a problem. The only time I would ever kill it is when I use it as a dew heater. I never bought the proper dew controllers and AC adapters and whatever. I just kind of rigged up, soldered, the cigarette lighter to the dew heater and just let it run. And it usually lasts about like an hour, hour and a half or so. So kind of my makeshift dew heater. But yeah, if you're going to work in the field, you definitely need something like this. I looked up even my own mount and how much juice it actually takes. When it's normally running, just regular tracking across the sky, it only takes half an amp. When it's full slewing, full speed, from left to right, it takes 1.5 amps. So 7 amps is way more than enough. Unless you plan on shooting from 10 p.m. to 6 in the morning or so, then maybe you might run into trouble. But like I said, this has never given me an issue. This is another fun toy that I got. Because my weakest link now has been my laptop. Again, shooting at home, I have all of the access to the AC and all that stuff. But when I go to the park, said the battery pack will last 7, 8, 9 hours, but my laptop lasts about an hour and a half. Especially when I'm running 2 cameras at the same time. My main camera that's doing the imaging, and sometimes I'll use the guide camera. So now you have that running at full speed, and it's just the laptop craps out. So I wound up purchasing this, and I don't know. I was a little questioning it. How could it do that great powering a laptop? But it actually does. When I go to the park, I usually start shooting around like 8 o'clock, 8:30 when I start going down. It won't even switch over to the laptop's power until about like 2 hours later. So I think this is pretty fantastic. I looked it up. There are some much cheaper than this, but this one's 27,000. I found one for 24,000. That was in like the $100 range, but I don't know. I really like this one because it has the AC adapter. I bought one originally that had like the barrel plugs, and it came with like 10 of them, but none of them fit my laptop. And then I was like, oh, should I buy another wire? And I was like, you know what? Let me just return it. I'll pay the extra, $40 or $50, whatever it was, and got the real deal.
So your computer's plugged into this battery, and your telescope and accessories.
Just the mount into the power tank.
Oh.
Yeah. There was actually another one. I forgot to put it on here. Whenever you buy like an LED strip, if you're putting it under your bar or countertops or whatever, they sell 12-volt battery packs. So now I figured that would be a good idea to use that for the cooling, because out in the field, cooling will take its fair share of power too, but it runs on 12 volts. So it just so happened to be the right connector, right fitter. So I put a piece of Velcro on top of my 8-inch tube, so the wire is long enough, and now I have the cooling out in the field, which is fantastic. Because I don't know if you remember the email I sent a few months ago, the difference between cooling, shooting at 20 degrees Celsius and shooting at negative 20 degrees Celsius. There's just a world of difference. So especially when I'm out in the field and want to show people a quick shot, I'll just max up the gain and try to do 30-second exposures, 45-second exposures. It tends to get a little noisy. So that was another cool toy, and very cheap too. That 12-volt battery pack is $35 or so. Okay, so now we're gonna get into the actual telescopes, and so there's three main kinds. So you got your refractors, your reflectors, and your compounds. The refractors, is what you think of as a telescope. Your Galilean telescope, just the same as your camera lenses. A few ups and downs for that. It's very lightweight, relatively. My refractor weighs much less than even my smaller telescopes. The optics are fantastic, but I guess that comes with a big but, because those range real drastically. Because if you have, I bought my guide scope, my 80mm Orion guide scope for maybe $100, but seeing is poor. It's good enough for a guide scope. Now, if you want to correct it, triplet, focal reducer, all that stuff, then the price could go up, 10 times the collimation. This could get a little annoying. It's not too bad with the compounds, but if you're gonna buy, one of these big guys, then collimation is gonna be a little bit of an issue. You know what the collimation is? Collimation is making sure that your optics are pretty much in line with each other. So you would not collimate these because you have your lens and it's coming into your camera, but that's all factory glued in, set. You really shouldn't be messing with that. Now, when you have a telescope like this, you're actually going to be breaking it down, throwing it in your car, taking it back out. So you're pretty much rebuilding this every night. And of course, you're not putting it in the same exact spot. So there are actually things like collimators, and they could get kind of expensive, that will line up. They'll give you like a red dot, and you have to start adjusting the screws on the bottom. Then you have a secondary mirror up here where light comes in here, bounces off the primary, bounces up here to the secondary, and shoots out here to the eyepiece. Now everything has to be aligned properly. So that could get a little frustrating and a little annoying. Collimation also happens on this guy, which is one of the telescopes I have, but it's not too bad. You have 3 set screws here on the secondary, and unless a year or two go by, or I'm driving down big bumpy roads, you're knocking it out of collimation, you really don't do much with it.
So that's going to be my question.
What?
Reflectors, do you guys come in often?
I mean, I don't have it up some but I think the Schmidt cast range.
Yeah.
I would say it depends on what you're trying to do. Like normally, no, you collimate it once for a little collimation. But they can get out of collimation. As you say, if you travel with it, it's going to get out of collimation, mess around a bit, and then you're probably going to have some collimation issues in terms of this heat expansion, or if it's outside or whatever. But it's small, right? And it depends on sort of what you're trying to do. If you're trying to do really like high resolution, high magnification, the collimation issue is going to be a much bigger deal than if you're just doing like large, like focal reducer and like basically, like DSO type work. You're not going to see as much.
Okay, so the downside of owning such a telescope or refractor, I believe it's extremely expensive for the size. Like, okay, my triplet was, well, with the focal reducer, about 350 millimeters or so, cost way more than my 8-inch tube at 2,000 millimeters. Of course, the optics are much better. It's much, more lightweight or whatever. But to create such great optics in a lens is very costly. A lot cheaper to make mirrors. Mirrors only have to be accurate on one side. It is much cheaper to make. Lenses, and these type of lenses are very hard. The other problem is they're not very compact. Now, these kind of fold into each other. So you see how the light comes in here, bounces off of here, bounces off of here. So the light, you could have a very high focal length, but taking a very minimal distance. Now, imagine if this wasn't folded up, and if your eyepiece was down here, this would be, 2-3 times as long. This would be a huge telescope. But because these guys have double mirrors, you start counting the focal length in here, bounces up here, bounces back here. It's called like folding in on itself. It's the light folding in on itself. So you can have much higher focal length at a lot less, less space. So about like I don't know, maybe an 80 millimeter, and a 90 millimeter or so might be the same length as a 2000, like a 400 millimeter or so focal length telescope might be the same length as up to a 2000 millimeter Schmidt Cassegrain.
Yeah, a refractor essentially has to be the length of the focal.
Yeah, it has to be straight. You're not messing with it at all, other than maybe a diagonal or so. But yeah, it's just going straight through.
A lot of it depends on what you ultimately want to, if you're going to do photography, what you want to take photos of.
Right. So this is kind of a fun thing, and you'll get it all the time too when you do an astrophotography. That bigger is better. It's always better. So I just had a conversation with one of my family members at a party, and I said, "Oh yeah, I got this new great telescope." He's like, "Oh, it's bigger than the last one?" I was like, "No, it's actually much smaller. It's like one fourth the size." He's like, "Oh, that's terrible then." So, well, no, because not everything is 2 arc minutes in size. So, yeah, like this shot right here was taken with the triplet and it's cropped. So right now with my the 2000 millimeter and my crop sensor, I believe I get something like this much in here. Yeah, which is way too tight for something that you want to kind of tell the whole story about. And the same with well, really all these. Yeah, Andromeda. That's oh my god.
One of the things to think about for a
That went way too
lot
far.
of you that are coming out of this DSLR world, right, is that the chip sizes that you're used to working with, you don't realize that they're very large chips. So one of the big problems with telescopes is that the actual image that's focused on your chip, right? If it's a good refractor, right, it'll have what's called an image circle that'll be fully corrected, which means if you think about it, the way that Tom has these pictures here, the stars,
There's way too many times.
the stars that are on the edges of these pictures, right, in terms of the chip, will be pinpoint, right? But if you have a Schmidt-Cassegrain or a reflector that's not corrected, which is one of the cheaper ones, right? The only part of the field that'll be corrected is the very center, and all of the stuff on the outside will actually, all your stars will look like comets because they won't be corrected.
Yeah, so this was taken with the 8-inch. So this is the crab. So and it's cropped as well. You can
Right.
see, you know, around here the
But
stars
if
are
you
a
use
little
an
more
AP
blobby.
If you use an APS size sensor on
Yeah.
this, then your sensor would be out to here, and all the stars out
Right,
here
right.
would be comets.
Yes.
Right? So one of the considerations is if you use your DSLR with a large sensor camera, you're going to be much happier with a small refractor, right? A small corrected refractor like that one there on the right hand corner, that'll cost you $1,000, right? This will cost you $1,000, and it'll be 400 milliliter. Or this thing will cost you $600, and it'll be 2,000, right? But this scope, if you're using a big chip, it's going to give you a lot of headaches. If you're using a small chip, like the camera that I use for the planets, then this one's going to be great. You'll be able to do a lot of focal reduction on it. You'll be able to get really good images. But there's another type of scope that is a Schmidt-Cassegrain. It's a more expensive version. It's called a corrected one, like the Celestron calls them the Edge.
Is it advanced coma free?
Yeah, and basically what it has these two mirrors, and it has a third mirror in the middle of the baffle tube, and that mirror corrects for what's called the aberration, the spherical operation. Those are a little bit more expensive. They're still cheaper than a refractor, but it's a little more expensive.
And the blue reflector is going to take a much bigger amount than the
Right.
refractor.
Yes.
So refractors, essentially, some of them are smaller than a lot of photographic lenses, lighter, especially with the camera attached to it, and then you can get a smaller amount, and then you can travel a lot faster, a lot easier with less equipment.
Yeah, so I'll give you a little history of where my astrophotography came from. So the reason why I'm a Schmidt-Cassegrain guy is because my father had a Schmidt-Cassegrain. So he had an 8-inch that after he had 4 kids went in the closet and stayed there for years. But I would drag it out every now and again, set up the mount, and look at Jupiter or what else I could find. So eventually I said, okay, I want to use this, but I want to get a real mount for it. So when I got my I got the Celestron AVX mount. It was the CG5 at the time, but I used that with my 5-inch Nexstar. Then I wanted to mount this and got the proper dovetails or whatever. Then all of a sudden, it's way too heavy for the mount because that mount could hold, I believe it was like 30 pounds, and this baby, fully loaded, focal reducer, my Canon 5D or whatever was getting there, was almost maxing it out. So that was my first pitfall. The second pitfall was I ran out and I said, okay, I was using my Nikon D3100 with this, which is a crop sensor. I said, let me get a full frame. I want to see everything that's going on the sides. I'm missing everything that's over here. So I got it. Everything out here was total garbage because I was using a non-corrected telescope. So looks great over here, a little worse, till almost just like unbearable, and then just like pitch black, towards the edges. So I said, okay, I went out and I spent $2,000 on a camera. I said, but I don't have a telescope that actually uses it. So I wound up cropping, maybe keeping 80% or 75% of the images, which, then why bother? You might as well just buy a crop sensor in the first place. So that was one of my big pitfalls. So that's when eventually I wound up selling the 5D and then getting the ASI 1600. So that's a crop sensor. So that's I've been much happier with that. Even this guy, not all refractors are full frame refractors. The one I got from Stellar View is good up to a crop chip. It's not really recommended for a full frame, but a lot are. So let's see. Okay. Yes.
So on a full frame, if you want to like you want to reflect or refractor, what's your recommendation of the diameter?
Well, it's funny because I believe the Williams optics. It's even you could even get maybe the 60 mm or so, and it is okay for a full frame. So it just depends on the type of telescope. So the one I bought from Stellar View, I think the next step up is everything else is fine for a full frame. So maybe that's how I got away maybe a little cheaper, with my 70 mm Stellar View because it was fine with just a crop sensor chip and not a full frame. If you wanted maybe the equal of that, you probably would have to pay an extra few $100s. But I'm not planning on upgrading my camera anytime soon. As and if I was, I got a few telescopes in mind too for that. So.
Remember, it sounds like you're ready to spend more money. William Optics, if you look on their website and just look at one of the telescopes, they'll have one of their charts and they'll show you essentially the image circle versus the different size frames from a full frame to various crop frames to the CCD cameras. So the image frame, the telescope has to project a circle that's bigger than the frame, because if it doesn't, it'll vignette or essentially cut off the image, and so you would need a sensor that's slightly smaller than the circle that it projects. And some refractors will project to have a full frame. William Optics website has some nice charts for each of their telescopes showing you the image projection size versus the rectangle frames of the different cameras.
All right, so now we're into the compound telescopes, like the Schmidt-Cassegrain. So this is pretty much the telescope I use. So, yeah, lighter than a Dobsonian, because a Dobsonian's pretty darn heavy. Portable, which I love, especially when taking out to the park at the AA stuff. No diffraction spikes. Now this is another funny one that may not thought of. Diffraction spikes happen when the light pretty much has to curve around any obstruction in your end. So you see how this is pretty much clear, other than the big secondary obstruction, and this is pretty much it's all clear. This light just goes straight through. But when you're looking at a Newtonian, a Dobsonian, you have these big support struts coming out here. So in this case, you have 4 big support struts. So when you take a picture, now all of a sudden your stars are going to have spikes around it, which could be cool, but it is a little bothersome to some people, especially if you have maybe you're looking for Pluto or something like that, and it just so happens to be cut into a neighboring star's diffraction spike, so you wouldn't ever see double stars and things like that. So that could get a little annoying. So, but there's no other way to hold this in there, not by magic. So something has to happen. The bad part about it is you're dealing with a big mirror, so your cool down is going to be much longer. And secondary mirror obstruction. So okay, you think you have this big space to deal with, but then they plop this big fat secondary mirror in the way. It does need collimation, but like Alfredo says, if you don't mess with it really too much, like I said, I really don't mess with it all that often. Maybe occasionally when I'm focusing on a star, you put it way out of focus, and then you'll see your secondary obstruction. It'll be like a big black spot, and the white around it be the star. Now if it's a circle inside a circle, perfect. If it's a circle and the other circle is like way off to the side, so then your mirror is not pointing at the right direction. Big problem I have, especially nowadays with all this rain and stuff, my telescope dews up almost immediately. You'll see when you take it out of your house and you set it up, and everything seems to go fine. And if you're a very humid day, and all of a sudden big sheet of water right on the front of your lens. And when that happens, you pretty much just got to pack it up and bring it in. You're not going to sit there, wipe it off. Some people, sit there with a hair dryer to try to dry it off. But in my experience, I said you could be wiping that all day long, and it'll just keep coming. So you just forget about it, pack it up.
What about the solution?
Yeah, so those are kind of cool. I have two of them. I have one for this big guy and one for my guide scope, which I guess I could use for the triplet as well. Although I haven't seen the triplet do up just yet. But it's nice. It's just pretty much, and I even made my own at home. Just pretty much resistors around a power source. So it's just like a heating coil around. So and it just straps around, has Velcro, a little stretchy. Just straps around the front here and just heats up the front of the tube, just like your car windshield will do. You know, when you get in. So it is helpful. I didn't buy all the pieces I should have, just because I guess I cheaped out on that. But you buy the dew shield, you buy the dew heater. I'm sorry, but it doesn't come with anything. So you also have to buy the dew controller. So the controller is what you could, raise and lower the power and also plug it into the wall. Because right now I have a dew heater with nothing. It just has, like a cigarette plug, a cigarette lighter. So that's what I'll plug into my battery pack when I'm at home and I'm not using it out in the field. And that'll last a little while because, heating up anything takes an incredible amount of power. Dew shields, yeah, so dew shields is just like putting a giant tube on top of this tube. So it's sort of like a lens hood. So it's just prolonging the inevitable that it's going to get you. So it'll give you a little extra time. Now, just the total reflectors, like a Dobsonian mount like this, um, they are incredibly cheap. I guess relative to their counterparts. Chromatic aberration, which is something that you deal with when you're dealing with lenses. Now, when you're dealing with lenses, all light doesn't bend at the same, wavelength. So your reds will go one way, your blues and your greens. So if you don't have a corrected refractor, that's not going to give you a heck of a great picture. So you can't get your red, greens, and blues all in alignment at the same time. So then you go to a doublet. So you have just your plain old, $100, guide scope lens. Then you go to a doublet, which is maybe 5 times the cost. Now that'll take your red and your blue and combine them together. So a lot of people use that. That's good enough, and especially if you're shooting with a mono camera, that's just fine. If you want to go even further, then that's when you get into the triplet. That could bring all the colors in at the same time. So that's why a corrected refractor is a lot more complicated, a lot more expensive to build. Because a mirror, just like a bathroom mirror, that light comes right back to you. Everything reflects right at the same wavelength. Downsides, as you can see, that this big monster, it's heavy. I would say extremely difficult, if not impossible, for astrophotography. Because imagine mounting this on an equatorial mount. It's just you really can't do it. If you have a smaller one, I see the 8-inch or 10-inch Orions have a nice one that you could put onto your mount, but it's very cumbersome. It's very big, very heavy. Frequent collimation, because this, especially this type of design, they make this so you could break it down. This is not going to fit in your car. So just like some of the guys we have out in Staten Island, they pretty much rebuild this every time they come out to the park. So you're rebuilding all the struts and whatever. So you're never putting that back the way you got it. So you have to fiddle with the adjustment screws and the mirrors and everything just to make everything lined up properly. Especially nowadays, you want to see Jupiter or Mars or whatever, which collimation is really important. The other problem is this is wide open. Every little piece of speck of dust and dirt and whatever's flying around that night is all landing right onto your mirrors. So it's just like this. This has a nice piece of glass here. Everything's nice and closed, so it should stay relatively clean. This is going to take some cleaning. The other problem is these are very fast telescopes, so they could be very fast, but you would need a corrector lens for this because your stars at the edges are just downright horrible. So if you were doing any astrophotography, this is something that would have to be a mandatory. Now, what a corrector does, let's see, is that my next slide? Oh, okay, I'll talk about that next one. Here's a little list of possible first telescopes that you may or may not buy. So other than Celestron, mine's a Meade, but I have a Celestron, a Meade 8-inch non-corrected, so 2,000 millimeters f10. So it's going on online now. You can get that for about $800. If you want it corrected, like the Celestron Edge or the Meade Advanced Coma Free, then you see how that jumps up to almost double the price. And that's all it's doing is correcting your stars out on the edges. Now this is what I use for my guide scope, the Orion 80mm. Nothing fancy about that, $110. You want a triplet Orion, let's see how much that jumps up. That jumps up to almost $1,000, almost 10 times the cost of a non-corrected. And on top of that, with the triplets, it's correcting for the colors, but you also need a corrector on top of it. And that'll be, I believe, my next slide. Now, the Mead, now this is a 10-inch. That's what they call this guy. This is the Mead Light Bridge. Non-corrected, 1270 millimeters, f5, so nice and fast, $700. So that's, that's almost the cheapest one on here, except for this poor guide scope. So I'd say this is a big bang for your buck, especially if you're doing visuals. Astrophotography, not so much, but if you're a visual kind of person, I'd say Newtonian is a real good bargain. All right, so focal reducers and correctors. Now this was an image I shared with the group when I was messing with the spacing. So you can see just how bad the edges, and this is with my brand new refractor. And I started to get a little disappointed. The problem was I didn't have the correct spacing between my reducer, but you could just see how bad your image could get. This is a polka dots I taped to the baby's crib on the other side of the other side of the house. But when you don't have a corrector, or you have the poor spacing, you see how your stars are nice and tight in the center, but how poor they are on the edges. When I first, I just, whatever spacers I had lying around, I strapped them, I ran outside, I took a couple of shots of, I believe it was Orion at the time, and I started emailing and said, is this supposed to be that terrible? I spent a lot of money on this telescope. This is horrible. That's something I expect out of my 8-inch. And then, we're fooling around and said, oh, you know what, so I got out the calipers and I said, okay, it's supposed to be X amount of millimeters away from the reducer. And so once I dialed it in, then this is the same exact picture, and everything nice and pinpoint from edge to edge. Problem is, some of these could be very expensive. I have a corrector reducer for, I bought the Celestron one, but I still use it with the Mead. That's a kind of a cheap one. I bought that for about like $100, $150 or so. The correctors that they have, the reducers they have for the Celestron Edge go up to $500, $600, $700. If you want the Celestron 11-inch or 14-inch, something like $550, $600 or so. So incredibly expensive, and that's just to drop it from f10 down to 6.3 or so. Yes.
Do you need reducers, correctors, for any type of telescopes, or like it's just for like SCPs or?
All right. So like I said, so this was my refractor, and I bought it special as the astrophotography package that came with reducer / corrector. I brought my native's 6.0 down to an f4.8. So it reduced it, but it's also a corrector as well. So not only are you now using a slower telescope, so f6, okay, not a big deal, but your edges look like this. And that's terrible. And that's what a very cropped sensor. The ASI 1600 is pretty cropped. It's a little smaller than what you would consider a cropped sensor. So you can imagine if you strapped the full frame onto here or so, it would just be atrocious at the sides. So that's why this is like a mandatory, at least for this type of telescope. Now with the Schmidt-Cassegrains, if you bought a fancy one like the Celestron Edge or the Mead Advanced Coma Free, or maybe some of the Ritchie Cretians out there that are the built-in correctors or whatever, then you might be able to get away with the native focal length. But again, a Schmidt-Cassegrain like Celestron and Mead are f10. That's incredibly slow. So if you want to try to take a deep sky object picture at f10, you're going to be taking a lot of time to do that. So I have actually tried it a few times. I said, okay, maybe I'll get a little more resolution out of it. It's a lot harder to guide, for one, because not only, at 6.3, I'm, at like 1200 millimeters, but now I'm trying to guide at 2000 millimeters. So I'm really increasing my exposure length, and I'm doing a lot poorer of a time guiding on there. So I'd like to say yes, it's mandatory, especially the Dobsonian's mandatory. So it's definitely a good thing to have, the corrector. All right, now guiding. So this is another whole box of worms. So you would think, okay, you spend hundreds of dollars or even thousands of dollars on the best mount that you could afford. Why would you need to auto guide it? Shouldn't it be good enough? Even if you dialed in your polar alignment 100% perfectly, even the best mounts could do maybe a couple of minute exposures at tops. And I'm talking about buying a $10,000 mount that the best you could do is about a minute or two or 3 minutes depending on your focal length. So why is that? So, okay, you dialed in yourself perfectly. You're asking your mount, say 2,000 millimeters, maybe 100 times zoom, 200 times zoom, to go perfectly, to follow this star from here to here over the course of 15 minutes, 30 minutes, and not move a single pixel. That's asking quite a lot out of engineering. So it's almost I'd say almost impossible. Although the new magnetic mounts they have claimed to do 30 minutes or 1 hour no guiding. So anywho, so you need guiding. You want to take multi-minute pictures, you need guiding. You could get away, especially with the new cameras. Maury does great work with no guiding, and he'll just stack 5-second images, 10-second images, because those he could get away with a decent polar alignment and a kind of shoddy mount that he has. If you want to go a little deeper, you want to take multi-minute, you're going to have to do some sort of auto guiding. This one here is the auto guider that I started out with. So this used to be called Orion's Awesome Auto Guider Package or so. So this still retails for about $350, but that's coming with the guide scope and the guide camera. So this is the Orion Starshoot Auto Guider, and I believe mine still works. It's a little finicky with the USB, doesn't connect just right, but it still works just fine. So I actually I use this for many years. Now, what is the downside with using something like this? Okay, so you're piggybacking it on your telescope, so that's adding a little extra weight. The issue is you're using a lot lower of a focal length than the main tube that you're shooting at. So what if you're shooting at 2,000 millimeters, but you're gonna auto guide at 100 millimeters, 200 millimeters? So you see the problem. This will pick up your errors, but you're so less zoomed in than your main camera. So by the time you're a pixel off on this camera, you're already 5 pixels, 10 pixels off on your main tube. So something like this they sell, but it comes with the warning like not to use past, I think maybe 1,200 millimeters or 1,000 millimeters or so, because it just can't catch the error before your main telescope picks it up. All right, so the next option. Well, you could always get a bigger guide telescope. So that's what I have. So right now, instead of this, I use the 80 by 400 Orion, and that works. That works just fine for my 2,000 millimeter telescope. This one has kind of always caused me problems. This off-axis guider. I think the big problem is because again, I'm using my father's old stuff, and the technology has come a long way. So what this really is a little prism in here that's stealing some of the light up to other camera. So think of, you're taking a picture, just your camera's on this end, your telescope's on this end. This is kind of siphoning off just a little bit of light to another camera. Now, okay, a few problems with that. On the upside, you're using the same exact focal length that the main tube is using. So you're shooting at 2,000 millimeters, you're guiding at 2,000 millimeters. So that's fantastic. The issue is you're using such a small piece of the window. So you have to hope that there's a star right here. Because, okay, this is your main picture and you're stealing this little square. So hopefully there's a star bright enough right here that you could pick up on. The fancier ones, like I believe this one is, you could kind of rotate it. That's something mine can't do. So if you can't find a star here, then you can just twist it around. So your main camera stays the same. You twist it around, and you're kind of looking for a star on the periphery. And remember again, you're going to use a poor, uncorrected Schmidt-Cassegrain. The stars that you're getting on the edges are going to be, your poor stars. The other issue, and this is the big issue that I'm having, is getting it to parfocal. Now, of course, my father bought this 30 years ago, so they didn't have the modern day CCD, CMOSs in mind, and I just can't get it close enough. So I'm gonna start bringing it to the grinder in the in the garage just to grind down a millimeter. I just can't get the camera close enough to get focus on both of the cameras at the same time. Remember, you're looking at the same image, so both of these have to be in focus with each other. So it might be easier with the newer ones nowadays because you see how these threads are on here. So that's made to just take your your ASI camera or whatever and just screw it right on. So that probably much better of an idea. So $130, not incredibly bad. Another issue that you might run into, especially with bigger full frame cameras, you're gonna see this in your image. So again, the one I have is a a very old one, a little poorer one. But I swear, even on my crop sensors, you do see a big shadow like right here, and you just can't get rid of it. So that's a very big downside. You're pretty much introducing an obstruction into your photographs. I believe they sell bigger ones that'll kind of avoid that if you're using a full frame camera, or at least making sure that your chip rectangle is not hitting this, but that's a little annoying. This to me is I don't know. I consider it the holy grail. Joe's the only one that I know that actually owns this one, and he's got his fair share of problems with this too. But this is called on-axis guiding. Now, what's really cool about this is it uses something called a cold mirror. So unlike this, you're not stealing a little bit of the light, you're seeing all the light. So it's using a cold mirror that it'll pass near infrared rays to your guide camera and reflect up your regular, what you want, your light, to your actual camera. So you're actually seeing the same image, just one is the near infrared spectrum, and your camera's seeing everything in the visible spectrum. So, well, as you can see, one big downside is very expensive, $1,400 just for this little box. But it does come with a cool, set of features. Some of these are electronic, that your guide scope is getting the same picture, so it has the software that says, okay, if the guide scope is out of focus, then your main scope is out of focus. So then it starts, adjusting your focus. I thought that was a really cool thing. A downside on it, at least it used to be a downside. I think a lot of modern day cameras can handle this, but it needs a camera that could see towards the near infrared. And according to the website, it needs 750 to 1200 nanometers is what that mirror allows through. So your camera hopefully is pretty good at seeing that in that spectrum. So if your camera is not very good at that the large end of the red spectrum, then you are getting the infrared, but your camera just can't pick it up. But I don't know. I think it's I think this one's a very cool, but very expensive. But this might be everything you ever needed in an auto guided package. You all use like the ioptrons, right, with your regular cameras and stuff. So what do you max out at? Maybe 30 seconds or 60 seconds or?
With the Sky Tracker, I've done as long as 1 minute.
Yeah.
With a 200 millimeter lens.
Oh, okay.
And I did like 90 seconds of Comet with
Uh-huh.
300 millimeter. I think it was set up properly. I didn't do a long over like an hour's worth. I did about 10 minutes. So I don't know what if we do it long.
Uh-huh.
But up to 200 millimeters, I found it to be fairly good. We're up to about a minute, definitely 30 seconds, 30 seconds.
Yeah.
And so that's pretty good. I mean, the package is pretty lightweight. My zoom is lightweight, and the camera.
Oh, that's great. Yeah, so I made a big deal about the guiding and so, but if you're using a lot less of a zoomed in, you're still having the errors, but you're not gonna notice it where a 2000 millimeter lens has to be pretty much spot on, and on top of that, having the guiding software in the background, making all the little adjustments. There's one other issue that you might come across, and I only bring it up because you're going to come across with reading it. So, and I've paid it no mind whatsoever, is the periodic error correction. I don't know if you ever, adjusted for that too, but I'd say it's something that happens in your telescope mount. You figure, yeah, it's running off of gears. Now, one of those gears is going to be slightly, larger, smaller than the rest of them. I guess where it loops around or so. So we figure maybe every 15 minutes or whatever the telescope cycle is, you should see a nice spike out of nowhere. Your telescope just going crazy just for a second, and then back to normal. So that's called periodic error correction. So nothing is going to, guiding or whatever. You could get really crazy with it and program it when it's supposed to happen, so your mount knows to counteract that. But I just bring it up just because it's a term that you're gonna see somewhere, and especially if you're beginning, you're thinking, oh, I had bad guiding today because of periodic error correction. So now you're gonna come through a million other problems before you even think about hitting something like that. But that's just the term out there, and it'll fall along the lines of, why is my guiding so poor? But I'll tell you, I've been doing this for years. I haven't even paid it the littlest bit of mind. And yeah, so it'll happen once every now and again, and maybe it'll ruin one picture out of your 10 pictures or so. But I wouldn't even bother unless Alfredo he had other issues with
Yeah, I mean, I mean, the modern scopes now are pretty easy to sort of guide, to sort of correct what I hear.
Yeah.
But, it's not something you're.
Yeah. All right, so the next issue, especially if you're shooting mono, filters are well, going to be mandatory. I shoot the one-shot color most of the time, so I really didn't have to mess around with this kind of stuff, but they really do come in handy. And these come in many different shapes and sizes, and what they can do and what they can't do. So let's look at like the most basic is your red, green, blue, red, green, blue filters. So if you're shooting with a mono camera, obviously you can only get a grayscale image. So the difference between a one-shot color and a mono is that Bayer matrix that's on your sensor. So there really is no such thing as a color camera. So everything is mono. They just slap on little tiny pixel-size filters onto each pixel. So really, using a one-shot color camera, you're getting a red pixel every 4 pixels. So you could think of it as actually less resolved than a mono camera, but it's a lot more convenient. Can you imagine using your DSLR as a mono? Imagine everyone standing at the same exact spot with you, red filter and a green filter and a blue filter. It'd be crazy. So that's kind of the reason why I don't go to the mono. It will give you a much better picture. Problem is you have to do that picture at least 3 times. And in a hobby, and especially fast paced, New York and New Jersey, whatever, and I might have an hour to grab tonight or so, I don't have the time to do, okay, I'll do half an hour of red, half an hour of green, half an hour of blue, half an hour of luminance or whatever, and then spend the time in Photoshop to start combining them all together. So that's why I like the one-shot color. But if you're gonna do the mono, then yes, then you have to invest in these, and these are relatively cheap out of the filter world. Your red, greens, and blues and such. Where you start to get a little more pricey is when you start to do like the light pollution correction. And if you're going to shoot in New York or anywhere near here, that this is going to be mandatory. You see these lines here. I got it into the next slide or so. Your sodium, your mercury, every street light or whatever is going to start ruining your picture in these types of wavelengths. So this particular oblong UHC ultra high contrast, it lets in this red, and it's blocking out these. So it should be blocking out some of the bad light that you want. Now nothing's perfect. It's going to be blocking out some of the light that you actually want, but you're overwhelmed with the city lights and the street lights anyway. So it's kind of a little bit of a trade-off. This is the filter that I've been using lately. Before, it's something called narrowband imaging. Now, okay, so this is a light pollution filter, but this still lets in quite a bit of light, like this whole big wavelength here and a whole big set of wavelengths over here. Now, when you do a narrowband imaging, it just lets in a very thin sliver, maybe 7 nanometers on the wide end, on the more expensive, really narrow band, maybe 3 nanometers worth on the low end. So see, these are how thin these strips are, incredibly thin. Now, normally, a few years ago with narrowband, you would need one filter for your hydrogen alpha, one filter for your sulfur, one filter for your oxygen, every different type of wavelength you get a narrowband image for. Again, having a mono camera is fantastic because every pixel is doing something. In mine, in the one-shot color, okay, so say I have a hydrogen alpha, which is this fella right here, this strip. What are my green and blue pixels doing now? They're doing absolutely nothing because it can't read. It's only looking for the red. That's with the filter. So I'm putting a filter on top of a camera that already has filters on it. So my red is getting a whole lot of stuff. My green and blues are doing absolutely nothing. And then the same thing if you did the oxygen or the hydrogen beta or so. It'll just be kind of the reverse. So at any time, I'll only have one of the 3 colors actually doing something. Now you can use that, and people have got some decent work with it, but really is meant for a mono camera. This triad filter, they actually made a filter that could let in this bandpass and these as well. So this is oxygen and hydrogen beta. So now all my pixels are at work. So that's what's really cool about this this particular. The only issue I have with this is hydrogen beta is a very rarely used narrowband filter. I think there's something like 12 objects out there that even shine in that particular light. So not super incredible, but it's still nice to have it working. You might come across something that says the Hubble palette. Now what that means is when you take your narrowband and you create a false color image. Now, okay, so say you have your mono camera and you take your 30 minutes of hydrogen alpha, 30 minutes of sulfur, 30 minutes of oxygen, let's say. Your hydrogen alpha and your sulfur are the same exact color. So you're going to put both of them into the red, or use something like a Hubble palette and start swapping the colors around. So you could do that with a mono camera. So you could say, okay, all these, this whole set of pictures was my hydrogen alpha, but I'm going to say that's blue. Although it came in the red spectrum, I'm going to tell Photoshop that's my blue. And then, take your oxygen and say, okay, that'll be my, that'll be my green, or that'll be my red, or, whatever. So that's how you create your false color image. And you might come across a lot of the same exact objects. They all have these crazy different colors just because, people, mix and match and swap them around. So that's one of my downsides that I would really love to do something with sulfur. I don't know if my camera would be all right with getting sulfur, but that might be my next purchase. I don't like to call narrowband imaging like light pollution suppression, although it does incredibly. It's just when the difference between using an actual light pollution filter and a narrowband image, a lot of things don't shine in those particular wavelengths. You're going to capture all sorts of stuff, knocking out these particular bad, sodium and mercury, street lights and stuff. You're not going to catch everything with this. Not even stars. Some stars will just, completely disappear from my picture using this. Galaxies, pretty much could forget about. There's a couple of galaxies that have, some nice nebula inside them, or, some shooting jets outside of it. But for the most part, narrowband for galaxies is, pretty much a, no deal. Just to show you, I got this off of yourlightpollution.com. So these are kind of the baddies that you want to, stay away from. This guy's particular bad. So this is what's going to ruin your image in the light pollution. So this is they're both oblong. Just happened to be a nice chart that I tried to line them up. So this is your CLS, your city light suppression, and this is your UHC, your ultra high contrast. Now you see both of them are similar on the high end, but it has a much tighter loop over here with the ultra high contrast. So it's just going to knock out just a little bit extra of these fellas over here on the fringes. So that's definitely something to look into if you're definitely going to be shooting anywhere near here. I have to go all the way down to Delaware to get a nice, beautiful sky that you can actually see the Milky Way from. So if you're going to shoot around here, you're definitely going to need something like this. Just to give you an idea of how bad it is a site called darksightfinder.com. So this is where we shoot down here in Staten Island. So this is Staten Island Park. So we got a better view than most. So this is where I lived in Staten Island, and you guys up here in Brooklyn and Manhattan are just pretty much off the scale. Oddly enough, though, my dark sight I believe is like a yellow or a dark orange, but the difference between here and here is amazing. I thought I was going to be way down in like the blues or so, but not even close. So that's kind of cool. So you gotta get kind of far away. I mean, this is pretty far away. Maybe you have to drive out, float out 30 miles into the ocean before you can start doing some decent astronomy. Buy a boat. Yeah. All right. So to finish up, these I think are the gimmicky nonsense. People show up with these fun little things, and it's like, oh man, you spent all this money on this nonsense. And maybe 10, 15 years ago, okay, these would be cool, but software and other freebie things could totally, get rid of all this stuff. In fact, one thing I forgot to put on here is ASI. They just come out with that ASI Air, and I saw it at NEAF, and it looks pretty cool, and it's not that expensive, and that hooks up, straight to your phone. So it's like, and it was a Raspberry Pi. I looked at it, I was like, this looks like the Raspberry Pi I play with at home. It's like, yeah, it's all Raspberry Pi just running off an SD card. And it's just like a circuit board sized computer, little credit card sized computer that's running off of some special software. And you don't need a laptop. It can run your guider, it can run your mount and all that stuff. And then you just boot up the software on your phone, and then there's your camera. There's your pictures. So this, for $140, is your GPS. So if you're too lazy to boot up on your phone, what is my longitude and latitude and what time is it? For $140, you can have it do it for you. This, I don't know. I've seen nothing but bad reviews, and I've seen someone fumble with this for hours, multiple nights in Staten Island. This is the Celestron StarSense. And what this does is you piggyback this on top of your scope, and you just say, okay, go ahead and align, So you don't have to do any work whatsoever. This camera is, going to detect what the stars are, where you're pointing, and then do it. And then you punch in your hand controller, and it points you to somewhere not even remotely close to what you're looking at. I think the problem is if this is not dialed into exactly where you're looking with the main tube, and then it thinks you're looking over here, but your tube is looking over there, so. And especially for $530, I'd say, definitely big no-no. Stay away from this guy. For another reason, other than the practical reason, is that I think it's a lot more rewarding to pull out a star chart, start, getting familiar with, oh, I know that star, and I know this, So I think it's a little bit, makes you a little bit, a little more rewarding for figuring out your way around the sky. Because if you just plop down your telescope, hit go, and then just go away for 8 hours and doing nothing, I don't know, find that a little cheap. And this is just Sky-Fi wireless telescope controller. So really, pretty much only controlling your telescope mount through Wi-Fi for $200. Where now the ASI Air I think was like $50. I forgot to look after the latest price or so. But yeah, so these, I think, total gimmicky, total nonsense. Don't even bother. Save your money. Definitely could be spent elsewhere on this hobby. All right.
Thanks, Tom.
Any questions on